Hi, everyone. Thank you so much for joining us today for the Integrity and Data Encryption ECN Deep Dive webinar. We'll go ahead and get started in just another moment here. All right, thank you all again for joining us for Integrity and Data Encryption ECN Deep Dive webinar as part of the PCI SIG Educational Webinar Series. I want to take a moment here to introduce you to our presenter. We have David Harriman, who is the Protocol Workgroup Chair for the PCI SIG and the Senior Principal Engineer at Intel. And I'll go ahead and pass it off to David.
Thank you, Megan. Greetings, everybody. First, we'll start with this lovely disclaimer. As you can see, it is important to remember that the material that we're talking about today is actually in a draft ECN that's currently in member review, so it is subject to change. So here's an outline of what we'll talk about today. First, we'll just talk a little bit about the background of the work we've been doing in security. I'm sure many folks here have already seen the CMA and DOE ECNs come out. We'll talk about the foundation that those provide and how they relate to IDE. Then we'll talk about IDE use models. We'll talk about the device's responsibilities in maintaining security and how IDE divides the responsibilities between various system elements. We'll talk about the next level detail in the IDE Draft ECN, which again is posted in the review zone. And then finally, of course, we'll talk about next steps. So first, why do we do security in this context at all? It basically comes from the fact that there are computational assets that have value. And they have value in many different kinds of ways, right? Sometimes consumers just want their data to be secret, maintained in a confidential manner. Other times, integrity is the essential thing. You don't want your bank account balances jumping around in funny ways, right? For businesses, it can affect their reputation. It can have very direct impacts on their ability to run their businesses by exposing intellectual property or damaging their business processes. And then obviously there are the governmental kinds of needs in national security, defense, etc. And so when we talk about computational security, we need to frame these kinds of problems as being holistic in nature. It's the classic, a chain is only as strong as its weakest link kind of thing. So what we're talking about here is a situation where the infrastructure really needs to be secured, edge to core, as it says here, right? And so here in PCI SIG, we represent an important link in that chain. But we also need to understand that it's a link, right? We're going to do our part. The things we're talking about today are, I think, very, very important tools for us to help build systems that provide a secure environment. But they exist in a broader context. And it's noted here, there are all different kinds of attacks that are interesting. these can be mounted in many different ways, and some of the foundational elements really focus more on things like supply chain. But we'll also talk here about how IDE fits in to address some of the issues that can come from malicious components or even software-based attacks. And as noted here, there's a lifecycle component to this, right? A component, once it's released from manufacturing, may go through many different uses, use models, owners. All of these need to be comprehended when we're talking about security. So to start with, let's talk a little bit about what are the specifications that we have already done and how do these fit into IDE. So on the left-hand side of this diagram, you see a number of different boxes, each one of which represents either a spec or a component of a specification. And one of the things that I want to call your attention to is that many of these boxes are green, which is used to represent specifications that come from the DMTF. And the DMTF is another SIG, separate from PCI SIG. And DMTF is providing many of the foundational specifications or important sort of related specifications for this work. So the primary one among those is the Security Protocol and Data Model, or SPDM specification, which is at the top. And DMTF numbers all of their documents, by the way. So it's a DSP 0274. And if you look for that on the internet, you should be able to easily find this. You don't have to be a DMTF member to download that spec, by the way. And what SPDM does is it provides a toolkit that allows, or I should say, defines protocols and mechanisms for a variety of security-related operations. Initially, the goal was to provide authentication and measurement features. And we've talked about that in some of our DEVCON presentations. And so hopefully, that's something that folks know a little bit about. I'll say a few more words later in this presentation about the importance of authentication and measurement, because they really are the foundation for establishing that your hardware is not tampered with and is what it is expected to be. Then we have the component measurement and authentication spec. That's a PCI SIG ECN. That's finished and posted in the specifications area. And what CMA does is it defines an adaptation of SPDM specific to PCI Express. So remember, SPDM, it's a very broad, very general kind of a specification. CMA narrows that specification and applies it to PCI Express devices and systems. Then one of the new elements here is the IDE key programming protocol. This is not a standalone specification by itself. It's actually an element of the IDE ECN, which is represented primarily by the box on the right-hand side. We'll get to the right-hand side in a minute. But the way that this applies here on the left-hand side is that IDE actually uses the construct of SPDM and some of these other technologies to provide a defined key programming model. Then what we see here as we go below that is that there are a variety of transports supported by these models on the left-hand side, and IDE actually supports using any of these. The one that's probably the simplest one to understand, because it's entirely within the PCI Express world, if you will, is this data object exchange, or DOE capability. And again, that's an ECN. It's already been published. You can download it from the specifications area. And it's essentially a register mailbox mechanism implemented in configuration space. So this allows host software to communicate directly with a specific function. That's one of the transports that can be used. But over on the left-hand side, we see DMTF has defined a way that SPDM can be operated over sort of a meta protocol called MCTP. And MCTP is itself essentially a transport agnostic technology. And so they define multiple transports, two of which are shown here, the MCTP over SM bus and the MCTP over PCIe binding. This is where they're actually using vendor-defined messages to transport MCTP traffic. Now, the way that these things all relate to IDE is fundamentally in two ways. First, this foundational ability to authenticate and measure the hardware is critical because there's very little value in establishing a secure link between components that are themselves compromised. Second is it provides mechanisms for establishing and programming the keys that will be used by IDE for the integrity and encryption mechanisms. And so what we get with all of these taken together is a complete spec-defined way to create interoperable hardware where all of these sort of management mechanisms for establishing the keys and establishing the authenticity of the hardware feed into what is really a freestanding capability on the right with IDE. And it's drawn this way because in some applications, perhaps those other things are not needed or wanted, right? IDE can be operated independently of the stuff on the left-hand side. But it means that you have to have an implementation-specific way of providing the keys and managing the keys. I already mentioned the status, but here are the links. The major call out here is, as noted, that the IDE ECN itself is in a draft status. This is an ECN to the 4.0 and 5.0 specs, and we're going to close member review in about 2 weeks here. And so I'm really hoping that we can get some, all of the critical member feedback rolled in that time, which is why this is such a timely presentation. And so it's my hope that fairly quickly after that, we'll be able to turn this around and get this published as a final ECN. All of the other items I talked about are already released. SPDM continues to be revised in DMTF. So, you should check back there periodically for revisions. And by the way, DMTF has a slightly odd way of numbering their revisions. It's different than the way PCI SIG does it. So if you see a letter after something, that actually means it's earlier than that number. So, think of the A version, at least if I understand their convention right, that would be like the pre-release version of the whatever number is being modified by the A. So, let's dive into IDE itself. So, first of all, why is it called integrity and data encryption? It's because what we're doing is we're providing a mechanism that will give integrity protection, cryptographic integrity protection, to transaction layer packets, TLPs. And the entire content of the TLP is integrity protected. Now, in addition, it also provides encryption for confidentiality to the data payload portion. And we'll see what that looks like in the packet format in just a minute. But the key point is this operates at the level of TLPs. It's been designed to retrofit as cleanly as possible into the PCI Express architecture. But of course, that means that we had to do a number of things that were, shall we say, interesting in order to make things work out. I'm actually very happy with the result, but a lot of what we'll talk about today is actually precisely those things that had to be done in order to make the cryptographic algorithms work nicely within this existing framework. We provide basically two kinds of protection. This is shown in the legend on the right-hand side. There's link IDE, which goes directly from one port to a connected port. I didn't show things like retimers here, but of course, every time you see a link, you should understand there could be a retimer on that link. We also provide something called selective IDE, and selective IDE is interesting because it can maintain security while passing through a switch. It's important to note, though, and this is illustrated in the little cartoon at the right, that when we talk about the endpoints or the root complex, we really are talking only about security to the edge of the component, just like is shown here in the cartoon. We're not providing security past that port. Right, that's one of the most fundamental concepts of IDE that might be counterintuitive in some cases. So this is not going into memories, either in the root complex or in the endpoint. It's not protecting any of those things. The silicon itself needs to provide security internally once you're past the boundary of the port itself. So what kinds of attacks are we focusing on? Well, basically, with both link and selective, right, we're providing protection for TLPs that are traversing between the ports, and we provide protection so that any kind of modification of the packet will be detected. Like I said, the data payload itself is encrypted. So an attacker who's using something like a logic analyzer or a traffic injector, we will be able to detect any attempt to modify the contents, reorder TLPs, add or delete TLPs. And again, of course, the data payload itself is encrypted, although the header is not, which is, again, something very important to understand. The fact that with selective IDE, we can also protect TLPs while they're going through switches is interesting in a variety of ways. One of the things is that it actually gets you out of some extra cryptographic work, right? Because if you're going hop by hop, like if you have a switch where, and this is illustrated in the yellow link connections that are coming off of that switch, you could send traffic over those links, but then the switch has to unwrap it, if you will, and then wrap it back up again at the egress port. By using selective IDE, the switch doesn't have to do that work, so there can be some advantages in that. And of course, you're also protecting the traffic against any sort of an attack from the switch. So the switch in that case doesn't actually need to be trusted. The algorithm that we're using here is AES-GCM, which is sort of the industry gold standard for doing this kind of data security. And it provides authenticated encryption. So the integrity and encryption functions are actually together in a tightly bound way. Now, let's look a little bit at how this actually applies to a TLP. And what I'm showing here on the top, of course, is just a single TLP. This is sort of the simplest case. And so as you can see, the entire TLP is integrity protected. The data payload, and that includes, by the way, the ECRC as shown here, and I should make a little bookmark about that. I just realized this slipped through. That would be encrypted. Now, I do apologize for this, actually. This figure is no longer accurate. One of the things that has been shifting around as we've been working through this is the handling of the ECRC. And actually, it's a good thing that we get to talk about this because I didn't include a separate foil on this. So the real value of providing a CRC check on the data is that if there is a bit error within the encryption or decryption engine itself, and those engines are large, those errors are very difficult to protect against in the data path. In other words, like with a data buffer, you could just provide parity or ECC and easily detect bit flip errors. The crypto engines, precisely because their purpose is to well, cryptographically obfuscate the data. It can be quite costly to add those kinds of checks in the data path. So one of the standard ways of addressing that is to take a CRC on the data before it's encrypted, and then encrypt the data and the CRC together. So the mechanism that we're actually going to use is something called a PCRC, which has the same polynomial as the ECRC, but is applied only to the data. You may recall the ECRC mechanism has some strange properties that come from the fact that we had to allow certain parts of the header to be modified in flight. That doesn't apply to the PCRC. So my apologies, the figure isn't quite accurate. And in fact, Megan, we should probably try to get that fixed in the posted version of the material. Now, the second diagram here, what this shows is something called aggregation. So one of the things that you'll notice in both of these figures is there's a MAC, right? So this is the message authentication code that is generated and consumed by the AES GCM algorithm. And in the way that the ECN is written, this is a 96-bit quantity. So 96 bits, of course, is a significant overhead. And there's also a TLP prefix that we're sticking onto the front of the TLP. So we're looking at 40 words of overhead for that when we're applying IDE to a single TLP. So the aggregation mechanism allows us to take multiple TLPs, each one of which still needs the TLP prefix, but we only use one MAC for the aggregated unit. So like in this case, although there are 2 TLPs, we only have 5D words of overhead for the 2 TLPs. And as written, aggregation can apply to up to 8 TLPs. It's also worth noting, as is in the call out here, all of these figures and what we're talking about here, these are all based on the released PCI Express base specifications. And if you've been looking ahead at what is happening in 6.0, then you know that we have to introduce new TLP headers. Fundamentally, the reason there is that we're just out of space. But we're also taking the opportunity in 6.0 to do a variety of sort of cleanup activities. And so as a result, of course, the TLPs will be laid out in a different manner when operating in flip mode. So the upcoming 0.7 version of the PCIe 6.0 base spec will include at least some material on that. Again, it's a little tricky because, of course, IDE not being a released ECN, it's a little bit awkward to refer to it in the base specification. But there will be some content there just to talk about how that works. It's also worth noting that one of the implications of that is that when a TLP is transiting a switch or going peer-to-peer through a root complex that supports peer-to-peer, that if it goes in, say, non-flip mode and comes out in flip mode, that's a problem because it's changing the layout of the TLP, which would be flagged as an integrity check failure. And so what that means, of course, is we just can't allow that to happen. So there will be some additional rules about translating between flip mode and non-flip mode when we get to the 6.0. So I've mentioned that one of the unusual things that we have going here is, of course, the need to retrofit these cryptographic capabilities into the existing PCI Express architecture. And one of the very foundational aspects of PCI Express, which actually predates PCI Express, is the PCI ordering model. So recognize that the table there on the right-hand side of this figure is familiar but different in some important ways. So first, I just have to step back a moment and explain something. If you're not familiar with AES GCM, this is an algorithm that has some sort of a counter. In our case, it's actually just literally a counter associated with each unit, in our case a TLP, that is processed, right? So there's, the concept of you have the counter for the first TLP, and then you increment the counter for the second TLP, and you increment it again for the third TLP, and so forth. That counter is needed at the receiver, and there are two ways of solving that problem. In some cases where AES-GCM is applied, the counter is simply sent along with the data. This is an undesirable overhead. The counter is fairly large, and so that would have added, to the bandwidth overhead on PCI Express, and so we never seriously considered doing that. It also makes it very difficult potentially at the receiver if things do come in funny orders, because then the receiver has to do some strange things to figure out, in some cases, what's going on. What we did instead is we recognized that with certain added limitations, we can actually cause the PCI Express traffic to flow in order, provided that we differentiate the three different flow control classes. Right, so we invented this notion of a substream. So the stream is the concept of the overall connection between the two ports. A substream is associated with the flow control classes posted requests, non-posted requests, and completions, which also then map into this ordering table, although in a slightly funny way because there are 2 rows and 2 columns for the non-posteds. And what you can see then we have done in the table is, and this applies only to IDE streams passing through a switch, is we require that the yes-no entries are simply treated as no. So what this allows is, of course, we still have to support certain bypassings because they're required for deadlock avoidance. So like posted requests can still go around non-posted requests. But within each one of these types, the traffic can't be reordered. So all of the posted requests, of course, come in order, but all of the non-posted requests also come in order. That wouldn't normally be a requirement, right? Non-posted could normally be reordered safely around one another. And so the substream mechanism, which is one of the more, I would say, subtle and potentially confusing aspects about IDE, is fundamentally designed in order to handle this retrofitting of AES-GCM, which really kind of wants the traffic to flow in order, with the PCI ordering model that would have allowed certain kinds of reorderings. Now, it is critical, however, to understand this is really just talking about a requirement applied at the hardware level, and it's applied to a specific stream. It would not be correct for software to assume this ordering model at the system level, because once you get past the boundary of a port, a component is still permitted to take advantage of, what would be allowed in the normal PCI ordering model without IDE. Likewise, attributes like relaxed ordering are permitted in IDE. They simply can't be used for reordering within a switch, right? But at the ultimate destination, which is usually where something like relaxed ordering adds value, it's still permitted to use relaxed ordering, and it works the same way that it does without IDE. So let's see. I'm going to just say a few words about some of these questions also that we've gotten in. Multicast explicitly disallowed. It's not explicitly disallowed, and you can see, again, in this ordering situation, how multicast could be very problematic. However, there are some circumstances where multicast can be made to work. And so I believe that the ECN actually has just a single line that says multicast is permitted, but essentially it's left as an exercise for the reader. I think I'll talk about some of these others a little bit later. Let me just push on ahead. So, we talked about how there are both the link and selective IDE capabilities, and this, of course, is the same cartoon that we were looking at a foil ago, 2 foils ago. Most of these things, I already spoke to, but I really want to reiterate that IDE is intended to protect the traffic between the 2 ports. Okay, this is a fundamentally different model than, for example, what a lot of people think of when they think of memory encryption. It's worth noting, by the way, that we do some things that typical memory encryption algorithms don't do. AES XTS, which is a very common memory encryption algorithm, for example, does not provide integrity protection. So, we're applying a different algorithm. We're providing some different capabilities, but the limit is it really does end at the port. And there were a number of reasons why this model made sense. But the first among them is that fundamentally, once you get into a component that is ultimately going to implement some sort of, let's assume it's the receiver, similar issue applies with the transmitter, it's going to apply some kind of a decryption function. And it's very difficult to know that it's implemented the decryption function correctly, meaning in a secure manner. At some level, you do have to trust the implementation of the component. And so, from a scope perspective, it's more reasonable to simply make the assertion that we're going to protect the TLPs from port to port, which can include, 2 ports that are separated by a switch if you're using selective IDE. But once you get to the destination, then you really are counting on the component to actually implement appropriate isolation mechanisms, which it might do simply through essentially access control, or it could do them using its own encryption type capabilities. That really becomes the responsibility of the component at the end. And I mentioned that you can use hop by hop with switches. And sometimes, like, for example, if you do want to do general multicast, you might want to do this, right? There are things that switches can do that will cause the traffic to be modified in interesting ways that would not work with a selective IDE stream. So that just simply means that the switch needs to be trusted in that case, which is really no different than the fact that you also need to trust the endpoints and the root complex that are involved in the IDE connection. So it's a kind of a give and take. I'm just going to pick off another question here. So there's a question, are host devices required to support both DOE and SPDM over MCTP? The answer is no. There may be some good reasons to support both of them, but they're not both required to be supported. There's a question here about aggregation and the max payload size. Yeah, so aggregation doesn't change anything about the max payload size. I think maybe what you're getting at is that if the max payload size is very large, then aggregating packets together could end up creating a fairly large unit. That's true, and it's just something that needs to be addressed at the component and system level. In a nutshell, actually, aggregation is a little bit painful, but again, it's one of the things that we've put into the protocol, recognizing the fact that we're trying to retrofit this architecture onto an existing architecture. And again, with GCM, typically you would try to apply the algorithm over the largest possible unit of data. But in PCI Express, it just gets difficult, right, once you try to go across multiple packets. Actually, the ATS question is a good one for this particular look here. Because, again, we're not going past the port, right? So even when we talk about selective and we're flowing through switches, mechanisms like address translation services and the associated address translation caching, those are orthogonal to IDE. And, you know, how do you establish trust in the endpoint? Well, that's really what things like authentication and measurement are good for, right? It's critical with ATS, and it always has been critical with ATS, that you're able to trust that the endpoint and the ATC are only going to do what they're supposed to do, right? Because otherwise, ATS, you know, provides a very direct way to bypass any sort of IONMU protections that the system might have. So IDE really orthogonal to that question, but authentication and measurement very central to that question, right? Because with authentication and measurement, we do provide a very direct way to protect those. Let me push on ahead, and then I'll come back and do a few more questions. And we should, by the way, have time for questions at the end, so I'll go back and make sure that we get everything answered before we're done. So when we talk about the system construction, you'll recognize, you know, this is the same system we were looking at before, but now it is annotated to illustrate what you could think of as the control plane functionality. And I use that term a little bit reluctantly because it's not quite an accurate way of talking about this. After all, we're still using all of the configuration mechanisms of PCI and PCI Express to define, for example, how packets are routed through switches. The base limit mechanisms, the bars, all of those are still as they are in regular PCI Express. And you could think of those as a control plane type of function. So I'm not talking about that kind of control plane, but here what I'm talking about really is the cryptographic control plane. How are the keys managed? How do you handle the authentication in relation to the keys? Because again, typically, you know, the way that you're going to want to do this, that you would only want to establish secured connection between components that have been authenticated. Now, you could, in some cases, authenticate components implicitly, like perhaps you just know by system construction that you have ensured that the root and the endpoint are not tampered with, that they are the way they're supposed to be. Again, that's allowed, but we also provide through SPDM with CMA, and again, you can use any transport potentially. It's a system question, which transport is actually appropriate. The mechanism at runtime to confirm that a component is in fact what it appears to be, that it's not been tampered with, that it hasn't been, for example, loaded with inappropriate firmware. And what we're illustrating here is that the same model that exists, by the way, for authentication and measurement supports cases where the management mechanism, if you will, is associated with the host and implemented as a part of the system software in the root complex. Could be firmware, could be OS, could be VMM, right? But something like that. And that's what's shown here with the green box on the root complex. And typically that would be implemented using data object exchange, right? Because host software has the ability to generate configuration requests. And typically it doesn't have the ability to generate, for example, MCTP traffic over any of the MCTP transports. It might, but in general it doesn't, and particularly from an architectural perspective, PCI doesn't define a way to do that. So if it does, that's kind of a root complex specific capability. A different way of doing it, which is shown in the sort of rust-colored box here, is that you could also have something, it could be a system management controller, BMC, or it could be, some security-specific kind of platform root of trust element that has some sort of an out-of-band management link, which, it could be that this management link is SM bus, in which case you'd use the MCTP over SM bus transport, or this could even be something like a PCI Express by one connection that would go, in addition to the primary link into the system. It would go from the system management controller around to each one of the components in the system. And in that case, you probably use something like the VDM transport. So, again, that's very flexible, but as a result, of course, there's relatively much less that we can actually say about it in the ECN. So what you'll notice in terms of how the ECN is written is that we've tried to be very crisp and complete in defining those mechanisms that work entirely within PCI Express. Mechanisms like these out-of-band paths are referenced, but they're not given the same level of detail in the specification, just because there's not really that much that we can actually say about it that's in scope for the specification. What this, by the way, so, it's the set and forget, probably not the best choice of words, but I couldn't think of a better way to say this. The basic idea here is that IDE supports models where, let's say that a system construction is very static. This, for example, might be very common in an embedded system environment. In that case, there may be no need to change any of the cryptographic setup during runtime, or at least the relationships between components, for example, typically wouldn't change the topology of the system. So in a case like that, you can essentially do what I'm calling a set and forget. So like you program up keys and you just kind of walk away. Now, we also support dynamic key updating. So without having to interrupt the flow of TLPs, it is also possible, both in the in-band and out-of-band models, to program new keys. I'll say more about that in a couple of while. While you're going. And then it is also possible, of course, as you might see in a like a server data center kind of a system, that you have things like hot plugs that change the system physical configuration at runtime. It's also possible, for example, in a virtualized system, that the security requirements would actually change dynamically based on how resources are being allocated to run particular workloads. IDE supports all of those different use models. Now, one of the things that I mentioned and kind of talked at sideways, essentially, is how there's a lot of important dimensions to security that really are outside the scope of PCI Express. One of them is this idea of the verifier. So, what I mean by the verifier here is that we've provided a way to demand of an element of the system that it prove its identity. This is authentication. But the problem is that the entity doing the verification may or may not have the ability to apply a very sophisticated policy here. And in any case, even a simple policy is outside the scope of PCI Express. So what we have is we have a toolkit, right? So SPDM with CMA really provides the toolkit. And different systems may have radically different requirements about the policies that they need to implement in order to have an acceptable verifier. Another aspect that's really outside of the scope here is securing any of these centralized functions. Like in the previous foil, right? What was illustrated is a model where keys are being programmed either by the root complex or by some kind of a system management controller. And obviously, if one of those entities is responsible for distributing all of the keys within the system, then if that entity is compromised, the entire system is completely compromised. So securing that entity is absolutely essential. And as I mentioned before, IDE does not flow past the port. We're not providing protection, for example, for system memory or let's say you have an endpoint with a local buffer memory. IDE does not protect those things. And, carrying that on, there are many ways that a device, and by the way, the same thing applies to the root, and it applies to a switch if you trust it. But, most people are, I think, principally going to be focused on endpoint construction, and the question here is, what does a device need to do in order to maintain security? Well, the first point here is that in this type of a context, even a very simple device has critical responsibilities that in many ways parallel the responsibilities of the host. It's not tenable to assume that a simple device can just ignore security requirements, right? Even very simple devices absolutely must implement certain foundational security within themselves. And again, some of these are outside of the scope of PCI Express, debug mechanisms being a classic example of something that just in order to work, essentially have to violate security, right? So how do you manage that? This is a very important question, but it's not something that we can directly answer. Likewise, when I talk about paths around encryption, this is a similar issue to what exists in a virtualized system today, right? Like if you have a function and you want to reassign it from one VM to another, the cleanup operation for the VM when it's being removed from the first VM, the VF, sorry, when it's being removed from the first VM, assumes that you're going to purge out of that VF all of the state from the first VM, so that the second VM can't read the state. So it's not really a new problem with IDE. It's just that the expectation of security is ratcheting up, right? Now, I've mentioned that the ECN itself is in a draft state. There are a few specific opens that I wanted to call out here, and again, we have a few weeks left in the review period, so it'd be great if people can, really focus their attention and make sure to get that review feedback in by the close of the review period. The first one is that the key programming protocol, which we've been trying to coordinate very closely with the work that's going on in DMTF, is still, frankly, something of a work in progress. We've already made some cleanup in the work group that's not reflected in the draft copy. But I think that the cleanup that we're doing is really just that. It's cleanup. It's not fundamentally changing the way that this works. So it's important for people to look at that, understand that, and really flag if there are serious issues. One thing, frankly, that's already come up is that we're not trying to provide a model for direct endpoint-to-endpoint key negotiation. There's a mention that this can be done. I think that that's, frankly, just a necessary compromise based on what we're able to define at this time, but it's clearly an open. Second, there's an area, and this is called out quite plainly in the text, where the work group had a number of questions related to key size. I mentioned before that we settle in AES GCM, which is kind of the gold standard for authenticated encryption. There was a little bit of discussion in the work group about what key size was appropriate, though. And there was a note. This is like a formally work group approved note that was included in the document. So please do take a look at that. And then there are a number of items that I think, again, we've actually made some good progress in the work group, tightening up a few things that in the current draft are maybe a little bit looser than we'd like in terms of managing how an IDE connection is set up, and particularly how it's torn down. Right? Once you establish IDE, how do you turn it off? is an interesting question. So that's an area where you should expect to see some improvement. But again, it's something where I think feedback from the membership would be very much welcomed. So, we've talked here today about IDE, and I'll go through the questions in just a moment. But obviously this is in review, and part of the reason to have this webinar at this time is precisely that we wanted to be able to catch the window of opportunity for SIG members to provide their comment and make sure that that comment is comprehended in the final version of this. I think that IDE itself provides a number of very exciting capabilities for PCI Express that we've seen a lot of interest in IDE. I think it's worth noting that a lot of this is also based on starting from authentication and measurement. So I do want to make sure that we don't lose sight of the fact that authentication is really a foundational capability to making IDE worthwhile. But I do think that IDE brings some very, very interesting and exciting capabilities. And obviously, this is something that we are in the process of developing. So really staying engaged, providing feedback, looking for the updates. Again, I mentioned that there are going to have to be some changes in 6.0 just because we're changing the packet format. That's also something that I think it's very important that the membership stay connected with. So let me start into some of the questions. There's a question about cable connections and how, from a physical perspective, cable connection, I think particularly the assumption here is that this might be either, within a chassis or potentially between chassis. And the question is, how do we perceive this risk versus a board level connection? And I think the answer is that fundamentally we don't see this as terribly different. Obviously, from a physical attack perspective, the easier it is to access something, the easier it is to attack it. Personally, I expect that most attacks actually would come from taking a valid device and compromising it. So in other words, finding a device that might generally be considered an acceptable part of a system, but then attacking the firmware of that device is probably one of the more likely kinds of attacks. But certainly, we do consider in-scope attacks where someone has physical access to the system. And in some cases, of course, what we're seeing is people are locating, for example, data center hardware in remote locations where they really don't have any physical control. So, I think it is a valid point that anytime someone has physical access, whether it's with a cable or a slot connection where they might use an interposer, we do consider those kinds of attacks to be in scope. And we believe that the protection we're providing will be quite robust in that case. Next question. So, can an attacker reorder substreams and construct an attack where writes are made visible before or after? So the answer to this is that all kinds of reordering attacks we believe are fully protected against based on the substream mechanism that we've defined. So first of all, one of the things that we have to recognize is most of these attacks actually would be violations of the PCI ordering model in the first place, right? And so when we structure the problem in this way, we see that the task for IDE is to guarantee that the PCI ordering model is in fact followed. So taking two writes and changing their order, or for that matter, just swallowing a write so that it doesn't happen, can be the basis for an attack. Obviously, bypassing a write with a read is another basis for an attack. And we protect against those kinds of reordering attacks. So we've tested this pretty thoroughly. I mean, again, since it is one of the fundamental parts of the protocol, excuse me, and since it is a little bit strange and unique to PCI, it definitely should get as much scrutiny as we can give it, but I believe it's quite solid. So there's a question about keys being rotated, and I think that, yeah, you know, I mentioned that there are use models, of course, where keys need to, for legitimate reasons, be updated, and we do support a system updating keys in an established IDE connection without interrupting the TLP traffic. That's the good news side, right? Now, there's the other side of that, which is how do you protect against an attacker inserting new keys into an established connection? And the answer is that the devices at the end need to monitor the connection that was used to establish the keys in the first place. And if that connection is suspended, then any attempt from that point to change the keys, like, you know, if you establish a new secure connection, for example, the device needs to recognize that this doesn't have the same security promise that the original one had, even if it appears to be the same thing. Simply the fact that the original session was interrupted and a new one established needs to result in IDE being shut down and taken into an insecure state. So the question is, comparing selective IDE and link IDE, why would you pick one or the other? I think that selective IDE does have some advantages, and in addition to ones that I mentioned, one of them is implied by the name. It doesn't have to apply to all traffic. So in a situation where performance is essential, and it's very critical to avoid that overhead cost that we get with the prefix in the MAC, it might be desirable to apply selective only to the traffic that strictly needs it. And so I think that that's you know, a plus on the side of selective. Now, a plus on the side of link, link is very simple, and it protects all TLP traffic. And if you consider that many systems don't even use switches, it's quite desirable to have a link connection in many cases, because it's just the simplest thing you can do. And it kind of enables, again, that set and forget model where you just establish link security, and you're kind of good from that point, because all TLP traffic will be protected. And let's see, I'm sorry, it looks like we're basically out of time. Megan is hinting at me that we should call it a wrap. There are a number of questions. So, you know, please do submit feedback if you have additional questions. You know, I guess I would say first, please do try to read the draft. But then if you can structure your feedback in the form of feedback on the draft, that would be great. And I promise you that the work group takes all member feedback very, very seriously, and we will go through all of it. So
great.
With that, thank you very much.
Thanks so much,
Megan,
David, and thank you everybody for joining us today. So these slides will be made available on the PCI SIG website, and then this video recording will also be made available on Bright Talks and the PCI SIG YouTube channel. So thank you all so much.